lecture we will discuss planar graphs and Euler's criterion to decide whether a graph is planar or not. Now, so far we have talked about graphs, and we have been drawing diagrams of graphs on a plane. However, we have not checked the issue that whether I can draw a graph on a plane without its edges overlapping on each other. For example, I can think of a graph like this, where these are the vertices and I have got two edges crossing each other. On the other hand, I could have drawn it on the plane in almost same way, just by drawing an edge like this. Now, we see that this graph G and the other one G prime both are essentially same, although if you look at this graph, no edge is overlapping with another, I mean cutting another. Now, our question is that when a graph can be drawn on a plane in this way and when it cannot be drawn in this way. So, we come to the formal definition of planarity of a graph. We write a graph G is said to be planar if there exists some geometric representation of G which can be drawn on a plane such that no two of its edges intersect. A graph that cannot be drawn on a plane without such a crossover is said to be a non-planar graph. Now, the question is that can we create some examples of non-planar graphs. In this context, there are two famous graphs called Kuratovsky's two graphs, which are shown to be non-planar. The first graph is the complete graph with 5 vertices, or written as k sub 5, and the second graph is written as k33, which is a bipartite graph, a complete bipartite graph with parameters 3 3. So, the complete graph with 5 vertices looks like this. We have got 5 vertices, V1, V2, V3, V4, V5. We have got a cycle here, and then we have to connect V1 and V3, we connect that. We have to connect V3 and V5, we connect that. Now, we have to connect V5 and V2, we connect that, and we have to connect V3, V2 and V4, we connect that, and now we have to connect V4 and V1, and now we see that neither can we go in this direction nor in this direction or nor in this direction without cutting one of the edges. So, I can write probably like this, and we know that there is an intersection over here. So, we see that we are unable to draw a complete graph with 5 vertices without intersecting the edges. So, I will draw it again. So, let us see the graph again. We have got V1, then V2, we draw like this, this is V2, then we draw like this is V3, and then we come back to here, this is V4, then we have got V5, and we join V5 and V1, and now V1 and V3 are joined, then V2 and V5 are joined, then V2 and V4 has to be joined. We can join like this, and then we join V3 and V5, and then we see that suppose I have to join, since we have to join V4 and V1, we have no other way other than cutting or intersecting one of the edges. So, we may write like this, or whichever we go we will intersect the edges. So, this is Kuratovsky's first graph, and let us look at the second graph. Which is, as I said, that a complete bipartite graph 3 3 and k 3 3. It has got the set of vertices is partition into two subsets each of 3 vertices, and then vertex from each vertex from one subset is connected to vertices of the other subset. So, I will have like this, then here like this, and then like this. In this context, we define bipartite graph in general. Graph, a graph G V E, a graph G V comma E is said to be a bipartite graph if V is partitioned into two subsets V 1 and V 2, where V 1 intersection V 2 is empty and all the edges are connecting vertices of V 1 to vertices of V 2, and there is no edge connecting vertices of V 1. So, we write that where V 1 V 2 is the empty set, and no vertex of V I is adjacent to another vertex of V I for I is 1 and 2. So, the vertices of V 1 are not adjacent to each other, vertices of V 2 are not adjacent to each other. So, now look, when we look at this graph, what we denote as K 3 3, we see that the 3 vertices over here are not adjacent to each other, and the 3 vertices over here are not adjacent to each other, whereas there are edges from one subset to the other. Now, this graph K 3 3 is something more. Here the cardinality of the set of vertices is 6, and cardinality of V 1 is equal to cardinality of V 2 is equal to 3, and if we note that each vertex of V 1 is connected or is adjacent to each of the vertices of V 2 and converse. So, we have K 3 3. It is a complete bipartite graph. We draw it again. Now, what we would like to prove here is that K 3 3 is not planar. Now, it is not difficult to check that K 3 3 is isomorphic to a graph like this. So, this I leave for exercise, that these two graphs are isomorphic. So, if I call this K 3 3 and this simply H, K 3 and H are isomorphic. Now, if I start drawing H all over again, then here, then we will start drawing the cycle over here, and then I can of course draw this one, and then see that we can choose to draw this edge from the top, but then if I want to draw an edge from here to here, then I am forced to intersect over here. This is the place where the intersection will occur. So, this graph also looks like a graph which cannot be drawn on a plane, but the proofs that I have given right now are intuitive proofs, and we would move on to prove to a proof which is more analytic. For that, we would like to have more definitions. So, first of all, we would like to mention that whenever we have a simple planar graph, we can embed it on a plane by using only straight lines. So, we do not have to have any crooked lines to embed a planar graph. If it can be embedded, it can be embedded by using a straight line, using straight lines. We do not give a proof of that, but it is very intuitive. And after that, we define a very important concept called regions in the context of planar graphs. So, a plane representation of a graph, a plane representation of a graph divides the plane into regions a region is characterized by the set of edges forming its boundary. Now, let us look at some examples. Let us look at a planar graph like this, which is reasonably straightforward kind of graph. Now, this is a planar graph, and we see that its edges are forming regions, and there is another region which is outside this graph. So, I can have regions which are both finite and infinite. So, if the region is enclosed by the edges, then it is finite, but of course, I will have one region which is infinite, which is intuitively outside the graph. So, here we have got 3 regions, let us call them R 1, R 2 and R 3. Now, we can remove this distinction between finite and infinite region by embedding a graph on a sphere, on the surface of a sphere, by using stereographic projection. Now, I will quickly give an idea of the stereographic projection of a plane onto a surface of a sphere. So, suppose I have got a sphere like this, where this is the south pole, this is the north pole, and I put the sphere on a plane, let us call this P, and what I do is that I take a point x on the plane and then connect x to the north pole, and it is bound to cut the surface of the sphere on another point, let us say x prime. Now, it is not difficult to see that whatever line or whatever set of points are there on the plane, in this way I can map it on the sphere, and this map is 1 to 1 and on to, except that I will have all the infinite points getting mapped to the north pole, rest of all the points are mapped to a single point, only there where whichever direction I go it will be mapped to the north pole. Now, it is again intuitively very clear that if we have a graph on a plane, I can use the stereographic projection to map it on a spherical surface and vice versa, and this gives us the theorem like this, which I will state without a concrete proof, but which is intuitively clear from what I have already told. This is theorem: a graph can be embedded in the surface of a sphere if and only if it can be embedded in a plane. Well, and the next theorem is again intuitive, that we will not prove, but state, that is, a planar graph may be embedded in a plane such that any specified region can be made the infinite region, can be made the infinite region. Now, we are in a position to start looking at a surprisingly elegant theorem by Euler, which connects the regions, number of vertices and edges in a planar graph. So, this is called Euler's formula, it states that a connected planar graph with n vertices, a connected planar graph with n vertices and e edges has e minus n plus 2 regions. Now, indeed this is a very surprising result, and we would like to give a proof of this result. So, first of all, we will observe that it is enough to prove this result for simple graphs. The reason is that suppose f is the number of regions, then if you see that if I start increasing the number of edges over a simple graph by introducing more parallel edges or self loops, we will see that each edge will generate an extra face, and therefore, if I have something like that f is equal to e minus n plus 2 for a simple graph. Suppose I have got a simple graph, and for this is true. If I introduce one self loop, then I am introducing one edge. So, e will increase by 1 and one region will also increase. So, this will increase by 1. Again I introduce one parallel edge, then again e will increase by 1 and f also will be increased by 1. So, if this formula is true for simple graphs, then it is true for any graph. So, therefore, we will only deal with simple graphs. Now, let the polygonal net representing the given graph has f regions, which we have already told. Let K p be the number of p sided regions. So, what we are saying here, that we can write a planar graph, if at all it can be drawn on a plane by the vertices and the joining edges as straight lines. Therefore, I will always be able to represent a polygonal represent a graph by a polygonal net. So, the faces will be polygons, and let us say that K p be the number of p sided regions, that is p sided polygons as regions. Now, if this happens, then we see that 3 into K 3, that is there are K 3 many 3 sided regions, and so the number of edges associated will be 3 into K 3, then similarly 4 into K 4, and similarly if we go on r into K r, and we know that each edge is going to be present in 2 regions. Therefore, I will have 2 times E, and if I sum up all these face sides, so they will give me ultimately number of faces, because k 3 is the number of faces or regions with 3 edges and 4 and so on up to some r. So, therefore, if I add all of them, I am going to get the number of regions, or which is sometimes called faces. So, I have got two expressions over here, and I also know that the sum of the angles subtended at each vertex is 2 pi n. Sum of the angles subtended at each vertex is equal to 2 pi n. Next, sum of the interior angles of a p-sided polygon is equal to pi p minus 2, and sum of the exterior angles is equal to pi p plus 2. So, in that network, that polygonal network of the graph when drawn on a plane, we will have f minus 1 bounded regions or finite regions and 1 infinite region, and therefore, if I sum up all the interior and exterior angles, then I am going to get a sum like this: pi into 3 minus 2 k 3 plus pi into 4 minus 2 k 4 plus and so on up to pi into r minus 2 k r plus 4 pi, and this is going to be equal to 2 pi e minus f plus 2. This is by using these two expressions, and this is equal to 2 pi n, and from this we get e minus f plus 2 is equal to n, which implies that f is equal to e minus n plus 2, which is Euler's formula. Once we have done this, we will check one corollary to this formula, which says that in any simple graph with f regions, n vertices and e edges, where e is greater than 2, e is greater than or equal to 3 by 2 f and e is less than 3 n minus 6. Now, let us try to give a proof of this result. Now, what we observe here is that suppose I have got f many regions. Each region will have at least 3 edges, and so the total number of edges is 3f, and we know that each edge will always be in 2 regions. Therefore, twice of E has to be greater than or equal to this, which proves this result. Now, if on the other hand we put the Euler's formula over here, we get f is equal to E minus n plus 2, then I get this is equal to thrice E minus thrice n plus 6, and which gives me, after reduction, E is less than or equal to 3n minus 6. Now, if I now look at K 5, that is complete graph with 5 vertices, here I will have E is equal to the n is equal to 5, n is equal to 5, E is equal to 10, and therefore, I will have E one side 10 and the other side 3 into 5 minus 6, which gives me 9. So, I have got 10 is less than or equal to 9, which is a contradiction, and therefore, it cannot be a planar graph. If I now look at the second graph of Kuratowski, we will see that this is K 3 3, and so I will have E is equal to in this case E is equal to 9 and n is equal to 6. So, if I now put in this value, when we will get 9 is less than or equal to, this is 3 into 6 minus 6, and this gave me 12. So, there is no contradiction over here, but I think a little more, I look at the graph again. So, I have this graph, and we observe that no region in this graph can be bounded by 3 sides. The reason is that it is a bipartite graph. So, if I start from any vertex, if I come to another vertex, it is on the other set, and then I go back, it is again the same set, and now I can never have a connection like this. So, I will never have a face which is bounded by 3 edges. Therefore, I will have twice E is greater than or equal to 4 times f, and which implies that twice E is greater than or equal to 4 times E minus n plus 2. Now, if I put E equal to 9 here, I get 18, and if I put E equal to 9 and n equal to 6 plus 2, then I will get here 4 into 5, that is equal to 20. Now, this is a contradiction, and therefore, K 3 3 also cannot be a planar graph. With this, I end today's lecture. Thank you.